Hello friends, Mr. Burrell here. We're nearing the end of our right triangle trigonometry unit. We've talked about sine, cosine, and tangent, and we've talked about how to use sine, cosine, and tangent to find missing side lengths and missing angle measures of right triangles. So in this lesson, we're just going to extend that into some real-world situations, some actual life situations that we could solve problems associated with using what we know about right triangles and sine, cosine, and tangent and trigonometry and all that jazz. So nothing terribly new today. We're just applying what we've learned to some real-world problems. So by the end of class today, these are the things I hope you are able to do. I want you to be able to use what you know about sine, cosine, and tangent to solve some real-world problems. Okay, we'll look at several examples of real-world problems that you could use right triangle trigonometry to solve. So first of all, in the real world out there, in the different careers that use right triangle trigonometry and need to take different angle measures and use that, I've included in the slideshow just a couple examples of some of those instruments. So you see here, like in the architecture world, they have this device that measures like certain angles depending on where they're standing so that they can get the correct heights and lengths for different measurements with houses, and especially with like really tall buildings and things like that. They have these really precise instruments that help them to make those measurements. Here's kind of more like an old school instrument that they used to use to calculate angles. You look into it up at a certain point, and this down here would give you at what angle you were looking up at that point. Here's like a higher tech version of this, basically, that calculates those angles. This is kind of like a level. All these different instruments that people use in the real world to calculate these different angles so that therefore they can use what they know about right triangles and trigonometry to solve for heights and distances and lengths that they might not be able to otherwise. So there are tons of examples of right triangles in the real world where it would come in handy to use trigonometry to calculate distances and lengths we couldn't otherwise. So a lot of like when you're digging into the ground or when you're calculating heights in the sky or of really tall buildings, it's really difficult to calculate those distances exactly. Like using a tape measure, you're not going to be able to calculate the height of the Empire State Building, but you might be able to use trigonometry to approximate that. So for each of these problems that we're going to solve, here are the steps we're going to take. We're going to draw a picture of a right triangle to represent the scenario. So whatever the scenario is, we're going to try to draw a right triangle that's going to model that scenario. Next, we're going to accurately label each of the parts of the right triangle. So with the information that's given to us, we're going to label the lengths and the angles and the things that we know. Then we're going to determine what missing part you're trying to find and what trig ratio you will use to find it. So am I looking for a missing angle? Am I looking for a missing side? And then what trig ratio, sine, cosine, or tangent, is going to be the most helpful in helping me to solve it? And then the last step, we're going to solve. We're going to use all the stuff that we've gathered to solve for the missing piece. So for example, according to the Americans with Disabilities Act, a ramp can rise no more than 1 foot for every 12 feet of horizontal distance. What is the maximum angle that the ramp can form with the ground? So this is an actual thing in the Americans with Disabilities Act. So ramps that are built going into buildings cannot rise any more than 1 foot for every 12 feet of horizontal distance. That's like to meet code to accommodate people with disabilities. So I'm wanting to know the maximum angle that the ramp can form with the ground. So let's draw a picture. So here's my ramp. Say here's like the doorway that I'm trying to get to, and here's down at the bottom of the ramp. So here might be like a right triangle to represent this situation. Here at the bottom of the ramp, here at the top of the ramp, okay? So if this ramp cannot rise more than 1 foot for every 12 feet of horizontal distance, this is going to be my rise. So that's going to be 1 foot. And then my horizontal distance is flat. This right here, I can't rise more than 1 foot for every 12 feet of horizontal distance. So it says, what is the maximum angle that the ramp can form with the ground? So here's my ramp, here's the ground, here's my angle right here. What is this angle? So step one, I drew a picture to represent this situation, I labeled all the sides with the information that I know. I know that I can't rise more than 1 foot for every 12 foot of horizontal distance. I've determined what I need to find. It's this angle between the ramp and the ground that I'm trying to find. So now let's determine what trig ratio I'm going to use. So if I put my thumb on this angle, this is the hypotenuse, opposite, and adjacent side. I can delete this door for a minute. I have my triangle. So with my adjacent and opposite sides, if I think of SOHCAHTOA, which trig function am I going to use with the opposite and adjacent sides? Well, tangent. So tangent of theta, the tangent of this angle, is equal to opposite over adjacent. Tangent of theta is equal to 1 over 12. Well, we just discussed, in order to undo tangent here, in order to solve for this angle, I need to take the inverse tangent of 1 over 12. So I'm going to grab my handy-dandy calculator, take the inverse tangent of 1 divided by 12, which gives me an angle of if I round to the nearest tenth, 8 degrees. So my ramp can't rise more than about 4.8 degrees. That's not very big. That's a pretty shallow angle. It can't rise more than about 5 degrees. And I'm done. That's it. What's the maximum angle that the ramp can form with the ground? About 5 degrees. Okay. Example number 2. In your guided notes, it says, to guard against fall, a ladder should make an angle of 75 degrees or less with the ground. What is the maximum height that a 20-foot ladder can reach safely? So, Mr. Burrell is out putting up his Christmas lights. Okay, here's my house. Here's the side of my house. And here's my ladder. I have this ladder leaning up against the house. See this? I don't need all the rungs, but here's my ladder leaning up against the house. Here's the ground. Here's Mr. Burrell about trying to climb up this ladder. So this ladder should make an angle of about 75 degrees or less with the ground. So here's my ladder. Here's the ground. So this angle can't be more than 75 degrees. It says, what is the maximum height that a 20-foot ladder can reach safely? So here's my ladder. The ladder that I have is 20 feet long. So this ladder is 20 feet long. And I want to know how high, say this is my house, right? How high on my house can I reach safely without making the angle too big? Because if the angle's too big, it's going to be like straight up and down. That's not going to be very safe. So let me erase the parts of my house here. So here I go. This is my triangle to represent this situation. I've drawn my triangles. I have labeled the sides and angles with the information that I know. I know that I have a 20-foot ladder. I know that I can't get more than a 75-degree angle with the ground. And I'm trying to find the height that I can reach with this ladder. So now, let's determine which trigonometric function I'm going to use. Sine, cosine, or tangent. Okay, well let me erase Mr. Burrell here. Here's the angle I'm looking at, 75 degrees. So this is going to be my adjacent, opposite, and hypotenuse sides. So it looks like I'm looking for x, the opposite side. I have the hypotenuse side, that's 20. So which of my trig functions has to do with the opposite and hypotenuse sides? Well, the sine. The sine function deals with the opposite and hypotenuse sides. So let's experiment with this. Sine of the angle, sine of 75 degrees, is equal to opposite over hypotenuse, x over 20. Okay. Well, sine of 75, my calculator knows how to do that. Sine of 75 is equal to 0.9659, and that's equal to x over 20. I'm going to write this over 1 just so I can have a fraction on both sides. And what do I do next? I cross multiply. X times 1 is x. 20 times 0.9659, let me do that in my calculator real quick, is 19.3 feet. So that's as high as I'm going to be able to reach with my ladder on my house is 19.3 feet. Any higher than that, it's going to start being unsafe. Okay. This one is pretty similar to one we've already done. I want to do this one. This one's kind of fun. This will be the last one we do together. So this example number 5, it says a camera in a room can only reach as far as 27 degrees away from the wall. If the camera is placed 9.5 feet up the wall, how close would you have to stay to the wall in order to remain undetected? So you're a professional art thief. You're trying to break into this museum. You're trying to steal some art, but you have to stay out of view from the camera. So here's my camera, and it kind of like swivels around, you know, and it says it can only reach as far as 27 degrees away from the wall. So this camera away from the wall, I can only reach about 27 degrees away from the wall. Okay, I can see all of this stuff over here, but I can't see like this chunk. My camera doesn't get that close to the wall. Okay, so if the camera is placed 9.5 feet up the wall, so right up here, this distance right here is 9.5 feet. That's how high up on the wall my camera is. How close would you have to stay to the wall to remain undetected? So here are you. You're crawling on the ground, you know. You're down here on the ground trying to remain undetected. You got your little Sherlock Holmes hat, you know. You're trying to steal some art. That wouldn't be Sherlock Holmes hat. You're trying to stay as close to the wall as you can, but you want to steal as much art as you can. So how far away from the wall, this distance right here, how far away can you get without being undetected? Without being detected. Okay. So there's my triangle. There's this little triangle of space that the camera can't reach. This angle is 27 degrees. This missing side down here, the distance away from the wall, I'm going to call x. And then the height that the camera's up on the wall is 9.5 feet. Okay, well, I've drawn my picture. I've labeled my sides with the information I know. Let's determine what trig ratio I'm going to use. So here's the angle I'm concerned with, this 27 degree angle. So this is my adjacent, opposite, and hypotenuse sides. So it looks to me like I have x here, 9.5 feet here. Which of my trig functions, sine, cosine, or tangent, deals with the opposite and the adjacent sides? SOHCAHTOA tells me that tangent is the function I am going to use. So tangent of 27 degrees is equal to opposite over adjacent, or x over 9.5. Okay. Well, tangent of 27, I can type that in my calculator. That's 0.5095 equals x over 9.5. And I'm going to write this over 1 so I have a fraction on both sides. Well, what do I do next? I cross multiply. X times 1 is x equals 9.5 times 0.5095 gives me about 4.8, not 4.5, 4.8 feet. So I have to stay pretty close. Me, Mr. Burrell, can't even lie down flat against the wall and remain undetected. I have to stay pretty close to the wall, within 4.8 feet, in order to remain undetected by the camera. Okay? And that's it. That's all I have got for you today. Hopefully, seeing some of these real-world problems, first of all, gives you an idea of some of the real-world scenarios that we can use right triangle trigonometry for. And hopefully you have a little bit of practice now being able to draw the triangles and recognize the trig functions, sine, cosine, or tangent, that we can use to solve these different problems. So I hope that was helpful. Please don't hesitate to reach out to me if you have any questions whatsoever. I hope that you enjoyed that as much as I did.